Hello, hello. It is time for lecture 23. If you are flipped in your video, or I am, it's actually lecture 23. That's right. Why is lecture 23 cool? 23 is just a cool number. It's a prime number and all that. In fact, there's a TV show that featured something called Network 23. Does anyone know the 1980s TV show that featured the thing called Network 23? Well, whether or not you do, you can easily look it up, right? It's no problem. I mean, I'll bet you if you just type in Network 23 TV show in some kind of search engine, you'll almost immediately get that it was Max Headroom, something called 20 Minutes into the Future. You'll also find out that that name was used later on for various other kinds of interesting projects and was even used ahead back in 1981 by a band called Tangerine Dream in their album Exit. Anyway, you see, it's so easy to just look something up, right? Well, all these fun things that I used to do, like I've been doing all semester long. Like if you know that song, let me know and you get a bonus point, million bonus points, you get an A or you get a letter grade, right? That kind of thing. It's fun, but you can just look it up as easy, right? So what's the point of me or any professor nowadays having you just type in an answer and look something up? I mean, it's useful to know the thing, but like, am I testing you on anything of significance? No. How are you better than a search engine? You're not. So the bottom line here is, remember, when you're taking this class or any other class and you're learning, ask yourself, how can you be better than the internet, right? What are you learning in this class, or how are you processing it into your knowledge and your big brain, like in a way that's more meaningful than something that can just, someone get an answer with a swipe of the finger, or in a subscription service that you pay a few bucks a month for, get the answer to, right? No point. So you want to be better than that. And that's my goal here as far as physics goes, right? Physics 1, this term is wrapping up. But what's more important is you'll be doing this kind of physics for your whole career, maybe your whole life, just because, regardless of your career, right? So have fun with it and learn. Learn these concepts and ideas to know how to make the calculations so that in the future you are more valuable than just a finger swiping across the screen. Okay, cool. Thanks so much. As always, it is lecture 23 and it's super cool because remember in lecture 22, we were talking about vibrations. I'm picking up good vibrations, right? And we have energy tied up in the wobbly, jiggly, rotationally, pendulumy, bang and forth kind of thing motion, right? In between atoms and different even molecules sometimes, right? You got chunks of matter tied together with these bonds, which you can then release for energy, like food energy, like calories with a capital C, or moving energies or heat energy with a little c, or mechanical energy in joules, right, which is all interchangeable. Remember that? Love that. That's another joule bites the dust. That's always too much fun to do. Anyway, now we're going to take those vibrations to the next level, because there is something that I am sure, that vibrations are really good at, that really help you enjoy or process the world around us, right? And that is sound. Anyone recognize what this is? Tuning fork. I don't know if you could hear that, because this computer system might actually have a high pass filter that thinks that that's noise, and you might hear it for a few moments and then it'll disappear because they'll say, oh, we want to filter that out so that you can hear me more effectively. I'll try it again, but just in case, right? You'll learn more about high pass filters and stuff like that in physics 2, which is a cool class too. And it's very easy to do with electrical systems or with optical systems to filter out higher frequencies. Anyway, we'll try this again. I whack my little thing that's got a chamber that will vibrate. What will basically happen is, watch. Okay, what happened? I can still hear it vibrating. Here's the deal. This thing, right, is vibrating. And just like how I was saying, the atoms in a molecule have got bonds in them, and they've got this stuff going through, right? They're attached. What happens to the atoms in this tuning fork? Well, when it has energy on one side, it causes a vibration within the system, right? Each of the little atoms and molecules is transferring energy back and forth and going wah, 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 like that. And eventually it makes this whole thing vibrate, right? It's an oscillation. like the simple harmonic motion that we've been talking about these past couple things, and the vibration and the twanging of this wonderful ruler where it's vibrating back and forth like that, that kind of oscillation. Well, if instead of back and forth a few times a second, if it back and forth, oh, hundreds of times a second, what'll happen is that this thing vibrating will actually start sending off its vibrations into the air. That's right. The vibrations don't just stay here. Most of the vibration stays in here, right? So it's in there and going whoa, whoa, whoa inside the whole line. But what it does is basically moving back and forth so fast that's causing the air around this tuning fork, right? All the tines of this fork, this whole thing, to start going out too and vibrating. And that, right? There's no boundary. It goes out into the air. Here you have a vibration, right? And it hits the boundaries of this and that and this and that. So it stays there. And so it vibrates this piece of metal, right? Exactly the way that we want it. But out here, it vibrates out into the air, and the vibrations just keep going because there's no limit to it. There's no boundary to it. So it goes on. And that, everyone, is a wave. When a vibration goes out without limit into a random direction or into many directions, you end up with a wave. And that wave is a disturbance. I mentioned this in the previous lecture, is a grave disturbance in the air, not the force, the air, but it can create a force when it hits something else, technically, and creates a force over a certain area. Oh, we've heard of that one before. What if a certain force, which is caused by the disturbance of the air, comes into my ear and it hits my eardrum, which is a certain area? Force over area. Oh, that's pressure. That's pressure. That's right. You create pressure waves in this vibration that comes out. Now, the pressure waves are very, very gentle. I know how we were talking previously about many joules, right? This is like microjoules, millions, even billions of joules of energy being transferred at any given second. Okay, not much at all. However, that's enough to create the vibrations in me that allow me to hear this. And hopefully, if my computer is not too stingy about its high pass filter, you can hear it too, right? Okay, one more time, just because it's fun. Oh, and listen to see if you can hear this thing vibrate too, because this has got a chamber, right? When I hit this, the outside will vibrate and interior will make a vibration as well. And so the air column inside will go whoa, 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 and maybe it will cause the sides and the lid of the jar, the bottom of the jar, to vibrate enough to create waves going out that way. So maybe you'll hear the waves coming out of here. Okay, so see if you can hear the vibrations of this creating waves and the vibrations of this creating waves. And now notice something different about them, maybe. Okay, let's give it a try. Did you hear that? Try again. Right. This vibrates, causing this to vibrate at the same frequency, but the first time I hit it, I went, "Tonk." Remember that? "Tonk." That vibration was one single pulse, right? That was a pulse of energy coming out. You heard that noise. That was energy, but it wasn't a sustained vibration. What you needed was something to vibrate for a long period of time. And this tuning fork is designed just to do that, to vibrate lots, right? And then notice it has its own tune, ding, up there like that. But then actually this thing sounds like this. Or if I had the right octave, it would be doot, like that, okay? That's 440 vibrations a second. That is how often you wind up getting this stuff coming out of the wave every second. So for those seconds while the wave is still going on, right, because this thing is vibrating so fast, you will wind up hearing this thing ring. And 440 cycles per second, for those of you who are interested in things like music, is the A above middle C. It is the note that violin strings are tuned, that piano strings are tuned, and very close to the note that woodwinds are tuned. Brass is tuned. Those are technically to a B flat, but you know, same difference. An A is an A is an A. Pretty cool, right? Okay, let's go to the OpenStax physics textbook so you can get a sense of exactly how those vibrations, how those oscillations to we refer, lead to hearing. And from that process, the concept of hearing, let's extend that point to the idea of waves. And once again, in a moment, we're going to borrow or ask the assistants, get the kind help of Diana Cowan, the person who did the AP physics thing also, right, for the simple harmonic oscillation. Well, she put together another high quality production thing with excellent description and so forth about waves. And so I want you to see that. So that'll help us understand. So this lecture doesn't have to be that much longer than about what we're talking about. And it'll get you a sense of what waves are, including the velocity of waves, what the frequency of a wave is, what the wavelength of a wave is, and all that cool stuff. Okay. All right. So here we go. Right to the textbook we go. OpenStax Physics, chapter 17. Let's see where that is. Is it here? Let's see. It is. Come on. It is, well, it is that page, but we're in a different location. This is section 30.6, which we will go to actually. If you're taking physics 2, or some equivalent next semester or some future semester, you will hear some of the stuff from section 30. Well, that'll be fun. But right now, let's go to the physics of hearing. Okay, remember oscillatory motion and waves. We're going to be doing that in a few moments. All right, you've already done some of that for the previous episodes and so forth. So here's the introduction to the physics of hearing. All right, and let's just go right to it so you can see what it looks like. I have my internet is taking its time. Hello, internet. Here we go. Move it along, move it along. So anyway, this college textbook, as we mentioned before, this college physics textbook is gigantic, right? It's like 1,500 pages long. So it's got a little bit of everything. If you want a preview of your physics 2 class, or if you just want to learn any kind of anything, you can go throughout this whole book and you can just read it and take a look. It'll be fun. I have done that a couple of times and I really enjoyed it. So here, introduction to the physics of hearing. This is obviously tree fell in the woods, but the question is, did anyone hear it? The question also is, if no one heard it, does it make a sound? The answer is yes, it did make a sound, because what sound is, right, is a longitudinal wave. It's that stuff of pulses, right, of the thick and the thin part of the air, the pulses through the air. There's a disturbance in the air that causes the motion to happen. And it turns out it doesn't have to be air, right? Waves, you've got these things: sound, frequency, and wavelength. And pitch is what we hear in our ears when we hear a frequency of a sound, right? And then sound level, you can have that thing. And you have sonic booms. You have this thing called the Doppler shift. That's great stuff. And then if you have something, just as I was talking about earlier, right, you have something solid or something cavity with a cavity in it, and it will vibrate over long periods of times, you can create standing waves. And those are essentially a kind of vibration, right, that moves back and forth in a closed system, in a bounded system, kind of like the metal piece of the tuning fork or the jar that it hit earlier, right? And all of that, you can make straightforward, simple calculations and understanding of stuff. And we're going to jump to 17.6 here, physics of hearing, because we're in our body talking about vibrations. And if you want, we'll go to ultrasound too. We'll talk a little bit about that, but that later. 17.6 is the part that you really want to pay attention to if we want to understand human hearing and the relationship between it and vibration. There also will be other videos that you can watch, including Diana Cowan's videos. There are some really good ones about how that works. Okay, so hearing is a perception of sound. And then when you learn about frequency and wavelength from the next part of the video, you can see the human hearing, right? If you have vibrations that go through the air, these waves that punch through the air, pulse after pulse after pulse, and if they do it 20 times a second, then you hear a very low grinding sound, kind of like the bottom of a piano kind of thing. But if you can go higher and higher and higher and higher, your ear can actually hear much higher than that, way up here, even higher, and high, way beyond what I just did in terms of my voice, right? Well beyond the piano, right? To very high tone. I can't even whistle high enough that you can't hear me, like, really, really super high. So it's a pretty high range, right? And then so when we perceive a frequency of this wave, it's called pitch. And we'll have that conversation. Normally, human beings do a pretty good job telling the difference between a 0.3% difference in frequency. That's actually pretty good. In other words, if you play a note on a violin and you play another note on the violin just a little bit off. If you've ever heard kids playing violin together and they're a little bit off, it sounds because it doesn't sound exactly harmonic and beautiful. But actually, that's still cool, right? Because it's basically energy and wavelength kind of mixing up together to get our sound perceptions. This is kind of fun, right? Again, the specifics of the waves you're going to learn not too long from now, but the idea of human beings hearing, right? Pitch being frequency, loudness, which has a sort of a relationship between how much power, how much intensity comes and hits your ear, as well as the frequency, whether it's a high pitch or a low pitch, will determine how loud you sense something to be, right? The note, basic unit of music, the tone, like whether it sounds like it's coming from lots and lots of frequencies together, or whether it's like one single frequency. And then what you have, the relative intensity of multiple frequencies is very similar to tone and timbre, right? So the difference in a tone, like whether you play a note on a piano that sounds rich or something that sounds like a staccato, or even more, like if you're playing something like a violin, for example, right? And it sounds really melodious, no, as opposed to, kind of sound like a scratchy sound. Like, what are those things? That's all in the brain, but we can tell. And by telling, we actually can enjoy music, or we can process sound. We can interpret what other people are saying, even if they're saying exactly the same word, right? Hello or hello, right? Different kinds of things. So anyway, measuring all these kinds of loudness and various intensity, that kind of stuff you can look at in a little bit, all right? And the difference between the loudness in fons and intensity in decibels. We'll be talking about that in the next lecture. And here is the part that we're going to talk about for the rest of this lecture. Well, not all the rest of the lecture, for the next bit part. This is a cross section of the human body's section of the skull where we have the ear, right? Figure 17.38 in section 17.6 of the College Physics OpenStax textbook. The soft cartilaginous part of the ear, this is all anatomy and physiology, by the way, so I know it's not true physics, but maybe you guys have already seen this before. The earlobe, okay, is actually called the pinna, and it acts like a focusing thing, right? If I've got, you should try this just for fun. We'll temporarily stop sharing. If I'm talking like this, right, I can hear myself well, but if I take my ears and do this, I can hear myself even better. Why? Because those pulses, right? Most of the pulses go right by me. They bounce off this screen or that wall behind the screen, and then they come back at me. And when they're bouncing back and forth like that, right, you wind up with a circumstance where most of it just goes off into the air and out there, and other people can hear it or not. But my ear catches some of it with my eardrum. Now, if my earlobe. Now, if I increase the amount that gets reflected, that basically that all bounces and then bounces back into my ear, right? So cupping your ear is the universal sign of, hey, speak up, please. I can't quite hear you. And it turns out that it's really, really effective. You should try this sometime. Cup your ears, and then you can see how much louder it is. But what's also cool is you'll notice when I talk, right? The sound doesn't just go into the air and then into my ears, out through the air. It goes through my bones, goes through my sinus cavities, my throat, my eustachian tubes, my cheeks, and it all goes up into my ear in all these different directions. So when I do this, it's not just that it gets louder, but it sounds different, right? Because I'm getting a larger percentage of the sound that's generated from my mouth in through my ear, as opposed to through the rest of my body. So when you do this sometime, just do that, face a screen or a wall or something and just talk, and notice that you will sound different when you do this as opposed to that. Not just louder, but different. Cool, right? Okay, let's go back to that drawing because it's a really nice thing to remember how the vibrations work. The ear, right? Here comes the vibrations, boom, 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 the pulses of the wave coming through here, the ear canal, which is often lined with wax, by the way, to protect it from the slings and arrows of outrageous air pollution and stuff like that. And it comes through this way and it bounces off the eardrum. The eardrum is a membrane in our body, right? That's only like a square centimeter. It's less than a half an inch in each direction. So it's a little round, mostly round. It's got also different, but it's just there. And it's like the skin of a drum. And those little air things just cause it to vibrate. But it doesn't just vibrate one way. It vibrates with many, many different ways. So every time you hear a sound, right, it can be something simple, like a simple tone, like a single note, or it can be like lots and lots of different tones all added in. Whether, for example, you drop one rock into a pond and you got ripples coming out of the pond, or whether you drop a whole handful of pebbles into a pond and you got this all different stuff, right? And so that processing of that sound comes in through here. And there are three little bones that are barely visible in this drawing. I'm going to zoom in a little later because down here, there's actually a better picture. This is the gross anatomy of the human ear. It's not actually gross, but you know what I mean. Gross being the large part. And then there's the detailed stuff, right? And what will happen is I'll show you the next zoom ins. Over here, the vibration gets carried from the eardrum through three small bones, often known as the hammer, the anvil, and the stirrup, because they three together look like parts of the kind of gear that people use to ride horses. The hammer, anvil, and the stirrup. And the stirrup is often known by its own name, the stapes, or the stapes, S-T-A-P-E-S. Tiny bone. I think I read somewhere it's the smallest bone in the human body. I couldn't tell you for sure because I'm not an anatomy physiology type person, but the vibrations of those bones, vibrations these are, right? Like oscillations, very much like simple harmonic oscillations of each individual thing, but it carries from one piece of material to the next, thus creating a wave that travels. And energy is given in a complex matrix of materials and vibrations, some loud, some soft, and it sends through eventually into the cochlea. And the cochlea, oh my gosh, I just got to zoom into the next part. Here's the schematic view of the eardrum, right? You got a force and a pressure times an area, right, coming in, and then the pressure times area is the eardrum, causes a force in the hammer. The vibrations in the hammer bone, right, gets transferred into the anvil bone, and there's a pivot, or, joint basically, connections between the anvil bone and the stirrup bone, and then the stirrup bone, stapes right here, right, the stapes, I don't know how to pronounce it, but anyway, that winds up going through to this oval window. And this complicated system. It's really not still 100% sure why humans evolved our hearing system to have all this extra complication. It works pretty well though, so it's interesting. There are some weaknesses. It's a thought process, but anyway, evolutionary biologists have a lot to say about that. So I have a friend who is actually a surgeon who does cochlear implants, and he does research on like human ears and how they evolved, and looks at similarities between human ears and whale ears and dolphin ears, and not just modern ones, but fossilized ones from millions of years ago. And it's great stuff. It's actually really, really cool. All right, never mind. Going a little bit further now, here's the inner ear. Once again, right, we got the hand. Oh, that's what they're called, the malleus, the incus, and the stapes, or stapes. I don't know. I got to hear somebody say that someday. Hammer, anvil, stirrup. And then you got the oval window, and you got air through here and liquid through here. And then you've got all these hair cells in the middle, these cilia. And those hair cells are standing along the edges, okay? And they're doing this. When the air goes by, they go boing, 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 boing. So you got your vibration again, you got your Hooke's law again. And so this got a little tiny bit of restorative force coming in. And so the cilia, as they wave through, right, like reeds in the wind blowing across a river, a channel. It's very romantic, but really it's physics. And what happens, you've got all these little things vibrating, and those vibrations get transferred through nervous system connections to the auditory nerve, which then goes into our brain, and then our brain interprets that physical force as electrical impulses, things like how we hear. Is that cool or what? Yes, it is super cool. Okay, so that's how basically waves go. And I want you to watch this later on. Hang on one moment. I will be right back. Okay, I'm back. Sorry for that brief pause. Although I know for you, there was no time. I had to take care of it. Anyway, bottom line, let me share my screen one more time. It's time now for you to go watch Diana Cowan's section, okay, of this discussion of hearing, but specifically about waves, because right now we talked about specifically how vibrations lead to waves, lead to our hearing, right, because of waves. Now you want to learn about waves fundamentally. Again, waves, light, and sound. This is the AP Physics 1 review with Diana Cowan. And Diana, when she does this, yes, this is supposedly AP Physics 1, but actually we are similar enough to it. Don't have to worry about the exam that that person, Diana, is describing or reviewing for, but the concepts are really well described and written out in this drawing, and she explains it well, in my opinion. So this is a really nice, and I want you to watch this and enjoy it, and so you can learn a little bit about things like the Doppler effect. You can see some about fast and slow, but mostly about some of the problems or questions that you might do to sort of know how doing things, and then traveling. And you're going to learn about light and sound. Okay, we're talking about sound right now as a kind of wave. We call that an acoustic wave. It's a kind of longitudinal wave. Transverse waves, on the other hand, right, is what light is. And then you'll learn about how fast a wave goes through and things like that. So transverse waves are very relevant to this, the simple harmonic motion. This drawing here from the previous lecture that we used, right? This blue line is an example of a transverse wave because the wave is going this way, right, through time, like that. And so the wave's going up and down and up, and the material is going this way. But notice that the motion of the material is perpendicular to the actual traveling direction, right? On the other hand, the sound waves that we were talking about, these acoustic waves, those are pulses, and they travel in the same direction. So it's like boom, 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 pulses going out, as opposed to up and down transverse waves going that way. So that's what you want to learn. Take some notes as usual, write down stuff in the lecture notes. I hope we've already written down some stuff in lecture notes here. We got other stuff to talk about in the lecture study guides. Okay, so that's what it is. And thank you very much for listening. I hope you're doing that sort of stuff. And remember, woo, good stuff. If you recognize that, send me an email. You get a point. Thank you so much. We'll see you in the next lecture, all right? Wave.